was the review day. All right, so Monday we went over what A did with this stuff, right? So we talked about A's role in these transformations, that was our stretching, our compressing. So if if absolute value of A is greater than 1, that's the vertical stretch. And then you're supposed to use that phrase, by a factor of da da da. Okay. And then if A is between 0 and 1, the absolute value of it is between 0 and 1, that's the vertical compression or vertical shrink. Gives compression. We also saw on Monday, if A was negative, right, that also could have that reflection, the vertical reflection or the reflection over the x-axis. I don't care which phrase you use there. I prefer that. Personally, I prefer reflection over the x-axis, okay, or vertical reflection. Okay, so then just digging back into our brains and saying, well, what did H and what did K do? But this is all stuff you guys have done multiple times. This should be the third or the fourth time we've talked about this. So this really should be, like, as far as describing transformations, you guys should be pretty set on this. Okay? So when we looked at a problem like x plus 3 squared, what did that plus 3 do to the graph? Addison, what did that plus 3 do to the graph? Dion, what did that plus 3 do to the graph? June? It's not up 3, Mason. Left 3. So Samantha, what did you have to remember to do there?
Like switch the sign, basically.
Right, yeah. So that was our left and right shifts, right? But darn old H, right? H is a liar. Okay. So inside the function, inside the radical, under the radical, those are our left and right shifts. Okay. So what if I throw on like a -2 there? So Mason, what's that -2 going to do to the graph? Down 2, right? So after the function, outside of the function is where our up and down shifts happen, but we trust K. Okay. So just paying attention, right? Is it under the radical? Is it inside the radical? That's left and right. Is it behind the radical, outside of the radical? That's our up and down. And then if it's in front, then that's the shifting, or that's the stretching, compressing, reflecting spot. A has 2 jobs, possibly. H has 1, left or right. K has 1, up or down. Okay. So pay attention to where it is. Okay. So that stuff should be really familiar for you guys. So you guys need to lean back on that. Okay. You should know that. Shouldn't be worrying about that. What I need you guys worrying about, what I need you guys focusing on, is the patterns of the variable, the patterns of the x values that you're going to be using. You really need to know those patterns. It's the ones we established last class period. Okay, but now I need you to start like internalizing them, saying when it says square root, I'm going to use these numbers as my x's. So when you read this problem, you say, oh, it's a square root problem. You automatically kind of click in and say, oh, that means I'm going to use these x values here. So what are those numbers? For square root graphs, square root functions, what values of x do we want to plug in? Close, Mason. Mason, what's the square root of -4? Yeah, right. 2i, right? We can't graph 2i. So it does have a square root, but it's not usable for us. We don't want to plug negatives in there, right? So normally we think that square rooting negatives is not okay. There's no real square root of those, right, Aiden? So no, it is perfect. Again, Aiden, if you said this in the public, it'd make easier sense for everyone else to understand what's going on. So there is a perfect square root of -4. It's just not real.
Oh wait, perfect means that it can be like perfectly divided up into whole numbers.
Yeah,
and then
there you go, exactly. Whole number or integers. Yeah, no decimals, no fractions. Yeah, that's what perfect means. So what are our other numbers? So we got 4 and 9. Oh, you had another one too, Mason. Sorry. Yeah, 0 and 1. No, sorry, 0 and 1. Okay, so these are our perfect squares. Okay, that's why we use them. There's nothing wrong if we plug in 5. There's nothing wrong if we plug in 7. We're just going to get a messier answer. Okay, but by using these numbers, we get the nice, pretty answers. Okay, we don't need a fifth one. Okay, I need you guys to kind of start internalizing that. It's a square root. Here are the 4 x values I'm going to use. 0, 1, 4, 9. My perfect squares that are below 10. Okay, I need you guys to put mental energy into remembering that. Okay, if that means you need to make a flashcard, you need to make a flashcard. Whatever you need to do to memorize that. Okay. I'm going to go ahead and plot those. You guys should be used to plotting this one right now. You did it a bunch last time on Monday. If you did the homework, you did a whole bunch. Okay. You should get that half curve off to the right. Remember we talked about that there's no arrow there. That's because of what we were just talking about with the imaginaries. You can't plug in a negative and get a real answer, so there should be no arrow pointing to the left. Okay. So I need you guys to know those numbers because that's how you're going to find these numbers. If you don't know those x's for the parent function, you're going to have a real hard time finding the x's for the transformed function. Okay. And what we're going to do is we're going to take advantage of this. So that says go left 2, right? Now this also says go down 4, but down is a y movement. It's not an x movement. Okay, and I'm trying to figure out what's going on with the x values, so I'm not going to pay attention to it. Okay, so I don't need to know that right now. What I need to know is how the x is moving. Okay, this graph is moving to the left 2. Okay, literally we're taking every point and we're moving it left 2. Okay, and that works pretty well sometimes. That's all I need to do that with. But when we start adding in shifts and stretches and reflections, it gets to be too much. If all we were doing was shifting up and down, we would have you guys just move the points. It would be really easy, kind of like you did in geometry. But as soon as you start adding in the reflections and the stretches, it just gets to be too much. So, okay. So instead, what we're going to do is look at this. If I'm taking each of these points and moving it left 2, what math would that imply if I'm going left 2? If you think about going left, June, what types of numbers do we define to the left of things usually? Like if you think about yourself right here, June, right? If you're at 0 and you go left 2, where did you end up? Yeah, you want to subtract, right? So we're going to subtract 2. So because it said left 2, we're going to subtract 2 to all those values. So instead of being at 0, we're going to be at -2. Instead of being at 1, we're going to be at -1. Instead of being at 4, we're going to be at 2. Instead of being at 9, we're going to be at 7. And we won't have a fifth point. Okay. Is anything not clear about how I did that? Because this really is going to be like one of the foundational things today is how you develop that chunk of x's. Brian, does that make sense? Raylan, does that make sense? Sophia, does that make sense? how I got those x values. Yes, I just subtracted 2, Jarrett. Yep. So if I want to find y's, sure. If I want to find y's, right? We find y's the same way we've ever found y's. We take our x's and we plug them in. Okay, so you have to know how to develop your x's so you can then find the y's. The y's is just going to be math. Okay, so I'm just going to be plugging in a bunch of stuff. Okay, so that's all I'm going to be doing right now is just a bunch of evaluating. Okay, so if I plug in -2, what do I get? So it's -2 plus 2 minus 4. Well, that's the square root of 0 minus 4, which is 0 minus 4. Oops. Which is -4. Then I plug in -1 plus 2 minus 4, which is the square root of 1 minus 4, which is 1 minus 4, which is -3. Square root of 2 plus 2. I'm going to stop writing it all out. Okay. 2 minus square root of 2 plus 2 minus 4, so that's the square root of 4 minus 4, which is 2 minus 4, which is -2. And then the square root of 7 plus 2 minus 4, which is the square root of 9, which is 3. 3 minus 4 is -1. Okay? So you're going to figure this column out by shifting this column. You're going to figure this column out by just plugging these numbers in. Okay? The same way you've always found y values, by plugging in x values. So I'm going to plot those 4 points. -2, -4. -1, -3, 2, -2, 7, -1. So I have those 4 points. It's the same shape as the last graph. It still goes from one point to the right only. So do not draw an arrow here. Okay, it goes from that point to the right only. Okay, so it's kind of like a starting point. With square root graphs, they have a starting point. It's not something we've seen a lot of. We had a vertex for the parabolas, and a vertex kind of for the absolute values. We have a line, we have the y-intercept, but it doesn't start there. Okay, but anything about how I got the graph? Okay. Domain is my x values. My leftist to my rightist. My leftist x value here is 0. My rightist is infinity. So from 0 to infinity. My range is my y values, the lowest value I have to the highest value I have. 0 is my lowest value. Highest value I have is infinity because it goes up forever, very slowly. For g of x, the leftist to the rightist. The leftist point is -2. The rightist point is infinity. So it goes from -2 to infinity. The lowest point to the highest point. The lowest point is -4. The highest point is positive infinity. So there's my domain, my range for each of those functions. Okay. If you notice where that -2 and that -4 came from, okay, shouldn't be too surprising where the -2 and the -4 came from. Oops. There's the -2. There's that left 2. Okay. We also see that -2 right there. Where did that -4 come from? There's -4. Here's the -4. That one doesn't lie to us, remember? And there it is again. Those 3 -4s are all connected. Okay, this little liar of a -2 and that -2 and then that -2 are all connected. It's not a coincidence. Okay, so you're looking at that. If you look here, you should also be able to match these. Okay, my left and right shifts affect my domain. My up and down shifts affect my range. This is pretty much what it's going to be like for these examples we're going to do today. Okay? The way we're going to find them. Is there anything here you want me to poke at more for you before we move on to the next one? Again, I'll just kind of yeah, you didn't know that. Which one? The black ones here, Brian? Or the blue ones? Black ones or blue ones? Blue ones, Brian. So these are the perfect squares that are less than 10. 0 is a perfect square, 1 is a perfect square, 4 and 9 are perfect squares. I could have plugged in 0, 1, 2, 3, 8 if I wanted. Okay. I was just trying to focus on ones that would give me nice answers. If I plug in 3, I'm going to get like 1.7. If I plug in 5, I'm going to get like 2.2. Okay. So we're just trying to plug in numbers that are going to give us nice answers. Okay. So we're doing, since it's a square root, we're looking at perfect squares. All right. Does that make sense, Brian?
Yeah.
Okay. So we move on to the next one. Okay. I look at the function. First thing I want to do is just identify what the function is. Okay. And once I know that it's a cube root, then it says, okay, well, that means I'm going to use these numbers. What am I going to use since that's a cube root? Tiam, what am I going to use since it's a cube root? Jordan, what am I going to use since that's a cube root? Addison. Tion, Jordan, Addison. I heard from you guys today. Good, June. -8, -1, 0, 1, 8. Okay. Those are perfect cubes that are between -10 and 10. Again, there's nothing wrong with plugging in -6. There's nothing wrong with plugging in 10. You're just going to get decimals, right? It's just more work if you do that. So what's the pattern of x values I should use when it's a cube root? What's the pattern of x values I should use when it's a square root? And it'll make things easier on you if you guys just know that. Because if you know that, then you'll be able to find this much easier. Okay? And in the end, guys, if you don't know them, you're not screwed. Okay? You're just going to have a little bit more difficult time graphing. Okay? Especially if you don't pick the right types of numbers for a particular graph. Like if all I do is plug positive numbers into here, I'm only going to get half of this graph drawn that I should. So I need to know that when I look at a cube root, I need to have positives and negatives. Okay, so it's just something to think about. Right? So just again, that memorizing start thing. That's the vocabulary. Cube root, okay, I better use my perfect cubes. What do those look like? Okay. And then again, you might get to the point where you just have these memorized also. That's not as necessary because you can always figure that out. What is the cube root of -8? Okay, it's -2. You can always figure out what the cube root of 1 is, cube root of 8 is. Okay, but you need to kind of know this. All right, then how do I figure out this? And where's our new function come from? Well, we look at how the old function is being transformed. Again, I want to look at the x part of things, the left and right part of things. So this is saying go right 3. So how am I going to move from here to here? What am I going to do? Yep, add, right, 10. So I'm going to add 3. Okay. So yeah, more specifically than just add, we want to add 3, right? So negative 8 plus 3 is negative 5. Negative 1 plus 3 is 2. 0 plus 3 is 3. 1 plus 3 is 4. 8 plus 3 is 11, right? So that one will just be a hair off the graph, but we can fit it. It's fine. Right? It's not like it's 15 or something like that. 11, 12, you should be able to graph easily enough. And the rest is a bunch of math, right? We got to plug those numbers in and see what we get. Okay, there's really no way around that. Okay, again, I'll write out a couple of them, but I'm not going to write out all of them. Cube root of negative 5 minus 3 plus 1. It's the cube root of 8, or negative 8, sorry, which is negative 2. Negative 2 plus 1 is negative 1. So negative 5 gives me negative 1. Cube root of 2 minus 3 plus 1. Cube root of negative 1 plus 1, which is negative 1 plus 1, which of course is 0. Again, I'm just plugging in the other ones. Cube root of 3 minus 3 plus 1. That'd be the cube root of 0 plus 1, which is 0 plus 1, which is 1. 4 minus 3 is 1. Cube root of 1 is 1. 1 plus 1 is 2. And the cube root of 11 minus 3 plus 1 is cube root of 8, which is 2. 2 plus 1 is 3. Oh. All right, I'm going to graph. I should have graphed the parent function earlier. I forgot. Sorry. But this one's kind of a pain because the graphs are kind of like right on top of each other. And so it just gets kind of messy to see it. If I can do this, what's that? What did I just do? Oh, that's what that did. Sorry. Okay. There's a way to. Okay, I'm actually gonna see if I can do this opacity thing so it won't be so dark. Make it a little bit more opaque. Ooh, that was good. You guys are in for a real treat right there. That was a good one. Okay. And then now I'm going to plot the other one. Okay. So on the back side of this, I'm not going to draw the parent functions anymore because the graphs are just, like I said, too much on top of each other. So it just kind of makes it a pain to have two graphs like this on top of each other. So I'm just going to stop doing that. We'll have seen it enough by then. And then 11.3 will be just, kind of over here by the R. Okay. So plotting those 5 point, they're real smooth. So this one's kind of tricky to draw. Let's see how I do this time. Flat on that left side. Head towards that 2, 0. That's where you start curving. Curve through there. Head off to the right. Not too bad. Might seem like I've been practicing that all day. So there's those two graphs. So, domain and range for cube roots. We talked about that. That one's actually really simple because it goes left forever, right forever, down forever, up forever. So domain and range for cube roots is always all reals. And when I say always, I mean always. So even though we've shifted it, it still goes left forever, still goes right forever, still goes down forever, still goes up forever. There's nothing you can do to change that. Okay? It's just how the function is. So that one should be easy to do. Anything here on the side before we go track up more? Braylon, you doing okay? Jordan, I haven't heard from you today. Okay. So just practicing the same. Again, things I want you to focus on. Right? The very first thing, most basic thing I want you to focus on is understanding which x's you're going to use. Okay, as soon as you look at the function, you know what x's pop into your head. Okay. So the very first thing you do is just, you're looking right there. Right? Is this a cube root or is this a square root? Okay. And so as soon as you know it's a cube root, it's those perfect cubes. Right? 0, 1, and 8, and -1 and -8. And that gives us 0, 1, and 2, and -1 and -2. I'm not going to graph that one. Okay. I can do the domain and the range real quick though. We just talked about that. It's all reals. Left and right forever, down and up forever. Okay. So that part really should be kind of be able to knock out pretty quick. Okay? But really what we need there is those x's. Okay. And if you're supposed to graph, then you would. Okay? But I don't want to just because it's going to be all on top of each other. Okay? So why do we do that though? Why do we bother figuring out those x's? Because now we can use them to help us find these x's. So what's happening to our graph here? What's that mean? Kalen, what's that mean? Cam, what's that mean? Ooh, Callie went all. Kyle went full force. Yeah, she saw the reflection. Saw the compression. That was really bad. Okay. Aiden. Okay, is that right too? Okay. But as far as what's going to affect those x's, it's only the right two. Okay. The reflection is going to flip the graph upside down. The compression is going to squish it down. That's a y effect. Okay. Only thing that's affecting our x values is that shift left or right. So I'm going to add 2 to each of those. Okay, so I got -6, +1, 2, 3, 10. And then from there it's a bunch of math. -1/2 times the cube root, -6 minus 2. And I'm only going to write out one of these, but then the rest we'll just do. 1/2 times the cube root of -8 equals -1/2 times -2, which is +1. Okay, so when I plugged in -6, I got +1 as my answer. I just need to walk through the rest of these. 1 minus 2 is -1. The cube root of -1 is -1. -1/2 times -1 would be +1/2. I'm just going to use 0.5. 2 minus 2 is 0. Cube root of 0 is 0. Half times 0 is 0. 3 minus 2 is 1. Cube root of 1 is 1. -1/2 times 1 is -1/2. So I have -0.5 there. Then 10 minus 2 is 8. Cube root of 8 is 2. Half of 2 is 1. -1/2 would be -1. Okay, so this is a compressed graph. If I didn't complain enough on Monday about how much I don't like compressing these, I'll complain again. I just don't like drawing them. They're so squished. They don't look like much. So 2, 0, 3, negative 1/2 right down there, 10, negative 1. Right, there's not much y movement. That's that compression. 1.5, and then negative 6, 1. Okay, so we should still see that S shape, except for now it's upside down, and then it's really flat, very, very flat. Okay. Okay, I mean, to us, it's going to look completely flat on the ends. It actually should be curving. It should slightly be angling down on the right, slightly angling up on the left, but it's so not angled at all. It's really, really flat. Okay. So it should look something like that. Range, domain. If I haven't made this clear enough, cube roots are super easy because it still goes left and right forever. Still goes down and up forever. Okay. Just because it's upside down, we always put the smallest number on the left and always put the biggest number on the right. Okay. You should never ever have a negative infinity on this side. You should never ever have a positive infinity on this side. Smallest number always goes on the left, biggest number always goes on the right, even if it's upside down. Okay. Anything there? I'd be doing great if it was you two in class. The other bunch of people, I don't know what's going on. There's 11 other people here on here that don't talk much.
I'm sorry, what did you say, Mr. Baker?
I said I'd be doing great if it was you two. It's the other 11 I'm worried about.
Oh, okay.
Addison, how's it going out there? Still haven't heard from you. Cam, still haven't heard from you today. Jordan, still haven't heard from you today. All right, last one of these. And the first thing I want to do is focus on is what's my function? What's my parent function? So I understand what goes on here. So Jordan, Cam, Addison, what numbers would I put over here? Mason, Brian, Caleb, what numbers are over there? Jarrett, right on. Jake, Jordan, Sophia, Tion. Good, Brian. Okay. 0, 1, 4, 9. Okay. And again, this, the f of x column, is important if you're supposed to graph both of them. I'm not going to do that this time, just so the graphs don't get all mixed up. Okay, but you need to know that right column, the left column, the x column, the y column can be figured out. Okay, and then the next columns get figured out. Okay, but you need to know that first one. Okay. So if we look at all the, if I look at all of the transformations here, okay. So we've got a reflection. We've got a stretch. And then what's that 3 doing? right? Yep. Up 3. Okay. Put that in the public chat. Okay. So what's going to happen here? So what do I put in this column? Yeah, not. You may mean the right thing, but you're saying the wrong thing. Okay. We don't want those y values. Okay. This one shifted right 2, so we added 2. Right. This one, shifted left 2, so we subtracted 2. This one shifted right 3, so we added 3. Okay. This one has no left or right movement, so we should have no movement here either. So we use the same x values. And we're not taking those points and shifting at all, so those x values don't move. Okay, we're not shifting left and right, so they don't move. Okay? Does that make sense? All we're doing is square rooting x, right? If we look real close, right, if we zoom way in, all we're doing is square rooting x. So what x's do I want to square root? I want to square root 0, I want to square root 1, I want to square root 4, I want to square root 9. Okay? I'm not, if I just imagine that was a square root, I'm not square rooting x minus 2. Okay? That's when I want to move everything to the right 2. Okay? So it's just the x that we're looking at. So just want those 0, 1, 4, 9. Does that make sense, June? So when I plug in 0, I get 3. When I plug in 1, I get negative 1. 4, square root of 4 is 2. 2 times negative 4 is negative 8. Negative 8 plus 3 is negative 5. Plugging in 9, square root of 9 is 3. Negative 4 times 3 is negative 12. Negative 12 plus 3 is negative 9. So evaluate those other points. So negative 4, square root of 4 plus 3, equal negative 5. Negative 4, square root of 9 plus 3 equals negative 9. Okay. So do the math, get the points. Zero, 3, 1, negative 1, 4, negative 5. This one's not too bad. If you did plot them both on the graph, they're not really all over each other. Remember, this is a square root, so there's no arrow on the left end. So we take that from that point to the right only. Even though it's right down, still just to the right. So it should look something like that. Domain for the parent function would be 0 to infinity. Range would also be 0 to infinity. For g of x, the leftist point, still 0, right? We didn't shift it at all. The lowest point is now negative infinity. The highest point is now 3. So again, that got flipped around. That's because of the reflection. Okay, so that reflection caused that range to flip around. Okay. I know we're pretty much out of time, but you guys, we've been talking about this the whole period, so this really shouldn't be a big deal. What's that negative do? What's the 2 do? What's the 3 do? Okay. So when you guys are doing this, it's just reflection over the x-axis. It's the vertical stretch by a factor of 2. It's that shift, left 3. Units. You guys should be really good at those. You guys have done those multiple times. All right, so here in C 6, we see both of them are cube root functions. What I see that's different about them, the g of x has a 2/3 in front of it and a +4 after it. So that 2/3 is in the front where a is. That's our stretch or compression. Since it's less than 1, it's vertical compression. I always want to use that term by a factor of. And then the +4 is outside of the function. It's not in the parentheses. It's not in the radical. That's an up and down. Since it's plus, it's going to be up. Shift. Number 7 here, those are both square roots. I see g has a -4 and a -1. So since the -4 is under the radical, it's inside the function. That's a left-right. Since it's lying to us, that's a shift right. 4 units. And then the -1, since it's after, outside of the function, that's our shift up, down. Since it's negative, it's down. And then last one here. So we got both cube roots. So that part's the same. This one has negative and a 0.5. So of course the negative is the vertical reflection, or the reflection over the x-axis. And the 0.5, again, is that compression, or stretch or compression, but since it's less than 1, that's going to be the compression. There you go. All right, see you guys tomorrow.